Hello everyone, and welcome back to another CIV 398 assignment tutorial. So in this tutorial, we're going to be covering question 4 of assignment 2. And just like question 3, it's actually not too bad, very quick question, and very dependent on Mathematica. So of course you can solve this by hand, but if you use Mathematica, this question will be a breeze, happen really fast. So the question's interesting because it says, considering the following matrices, and you got a matrix Q, which is just a mess. It has a bunch of fractions, a bunch of square roots, crap like that. And you got a matrix M, which is very, very nice. And being matrix Q, we can kind of already assume that this is going to have to be a transformation matrix because that's typically what we use it for. But just to be on the safe side, let's read the actual questions. So it says, Part A says, find the component Q in the coordinate transformation matrix Q such that the matrix is orthogonal and specify whether the matrix is associated with rotation or reflection. So if we look inside Q, there's actually a little small q that's unknown. So just like the previous questions, we're going to have to use kind of the properties of the matrices, stuff like that, to figure out what is Q. And second of all, or I guess not second of all, the way that we can determine that is a specific property and that Q is orthogonal. So we're going to use that property to figure out what small q is. And after we do that, we'll have the full matrix Q. And from that, part B says, let Q transform the orthonormal basis set B to B prime and determine the components of the matrix M prime in the new orthonormal basis set. So you guys have already done change of basis before. This is kind of second nature to you guys now. So once we have Q, finding M prime is not going to be hard. But then we're going to get into kind of the new stuff, and it says find the three invariants of M and M prime, and then comment whether they are the same. So a little spoiler alert, they should be the same, as we'll discuss. But yeah, a nice, easy question. So let's talk about orthogonal matrices, because this is going to be the key to part A. And if you don't get part A right, then all the rest is going to go right downhill. So let's look at the properties. So by definition, a matrix is orthogonal if Q transpose a Q is equal to the identity matrix I. And from this, we can conclude a bunch of other things. So one of them is the determinant of Q is equal to plus or minus 1. The rows of the matrix are orthonormal, so that means that all the rows in the matrix are perpendicular to each other, as well as the columns of the matrix. And finally, the product of two orthogonal matrices is also orthogonal. So if we look at this, well, we know that our matrix Q is orthogonal. Well, we're going to need an equation to solve for that little q. So let's kind of look down the list, and a lot of you guys, okay, well, I know that the determinant gives me a nice equation. We used it before in question 3 where we made the determinant equal to 0. We can solve. And that would be great in this question. But the problem is the determinants of an orthogonal matrix can be two different things. It can be plus 1 or minus 1. And since we don't know if it's plus or minus 1, we can't really use this. So what we're going to do is we're going to use this property right here, which says the rows of the matrix are orthonormal. Or you can use the columns. But for me specifically, I'm going to use the rows to show you guys. So considering that property, that the rows of the matrix are orthonormal, what exactly does this mean? Well, it means if I were to make a vector A, that's A1, A2, and A3, so the first row of that matrix, and another vector B, which is B1, B2, and B3 of this matrix, well, if I dot them together, it's going to be equal to 0 because these vectors inside of the matrix are perpendicular to one another. So if you guys are a little confused what I'm saying about these vectors inside of the matrix, I'm talking about this. So I can make three vectors, the first one A, which is A1, A2, A3, the second one B, which is B1, B2, and B3, and finally the third one is C, C1, C2, and C3. And if you guys remember in the question, or at least for mine, because remember, they're all going to be randomized, my missing value Q was C1. So A dot B isn't going to do me much good. However, the other ones will. So from this, we can create three equations. Just those are the three dot products above. So the first equation is if we do A dot B, and the second one's B dot C, and then finally the third equation is A dot C is equal to 0. And we only have one unknown, so we only need one of these equations. So again, if my unknown is C1, that's my value of Q that I'm trying to solve for, I'm going to have to use equations 2 or equations 3. Equation 1 won't give me anything because I already know all the values of A and B, so you can verify that it's equal to 0 if you're feeling courageous, but other than that, equation 1 is pretty useless. So again, just take one of these equations, we can solve for Q. So moving on from that, the second question is, it wants to know if Q is a rotation or a reflection matrix? What is it associated with? So remember that we said that the determinant of Q is equal to plus or minus 1, and that plus or minus is actually the key into figuring out this question. So if the determinant is equal to positive 1, so plus 1, Q is associated with rotation, while if the determinant is equal to negative 1, Q is associated with a reflection. So now that we have the full matrix Q, it's as simple as solving the determinant either by hand or through Mathematica, and you'll either get 1 or negative 1. And then you just check, okay, well, if I get a determinant of 1, Q is rotation. If I get a determinant of negative 1, Q is obviously a reflection. So that's just the statement here, just kind of summarizes what I just said. We can find the determinant to figure out what Q is associated with. So on to part B and part C of the question. So part B, I'm not going to really discuss. Change of basis, you guys know this already. We can find M prime through the formula stated there, where M prime is equal to Q times M times Q transpose. But the juicy part of this question lies in part C when we start talking about invariants. And invariants are things that do not change with the matrix even after a change of basis occurs. So I'm giving you guys the answer real quick to the second part of part C, which is the invariants of M and M prime are the exact same. But one thing you guys are going to have to do is calculate these invariants. So if I have the matrix A1, A2, A3, B1, B2, B3, and C1, C2, C3, the first invariant is also called the trace. So invariant 1 of M is equal to TR of M, which is the trace of M, and that is the sum of the diagonal components. So if I have a 3 by 3 matrix, it's A1 plus A2 plus C3. I guess not A2. I can't even talk. A1 plus B2 plus C3. So it's what I have in that red oval. We're just going to sum up that diagonal portion. The second invariant, a little bit more, not tricky because it's still pretty easy. These are all pretty easy, let's be honest, but a little bit more intuitive, is the second invariant, which is equal to 1/2 multiplied by invariant 1 of M squared. So keep in mind that that first invariant of M, that is squared. A lot of people forget that squared sign and lead to the wrong answer. Minus invariant 1 of MM. So once we have our matrix M, we multiply it with itself to get a second matrix, MM. So it's not that hard once you think about it. A lot of students will either forget the squared sign or they'll forget that it's invariant 1 of MM instead of just M. And finally, the third invariant, which is the determinant. So invariant 3 of M, well, that's just the determinant of M. So that one's nice and easy. You guys have dealt with determinants in the last assignment. You really got determinants shoved down your throat in this assignment. So by this time, you guys should be the master of determinants. But of course, you guys are going to use Mathematica. So let's look at the Mathematica commands for these determinants. So Mathematica, if you put something as M prime, it may not come out very nice. So what I said is let M is equal to M, Q is Q, and M prime is equal to M2. So if I write M2 in Mathematica, I'm referring to M prime. So the first operation that we have to do for part C is the change of basis. So remember that M prime is equal to QM times Q transpose. So what I did here is I put M2, which is the way I put M prime in Mathematica. And what I did is I did Q period M period transpose a Q. So two things that we're going to want to take note of is the first one is the transpose function. So if I need to transpose a matrix, I can just write transpose. So remember, any Mathematica function, I need a capital T and I need those nice square brackets. But here's the thing that'll get a lot of students. When we're multiplying matrices, the multiplication command for matrices is a period. It's a dot. If you guys go with the typical star sign, you guys will not get the same answer. If you're doing that, then if you use the star sign, I should be more specific, then basically you're just multiplying each component in the matrix by each other. You're not actually multiplying the matrices. So make sure that you're using the dots and not the stars when you're multiplying these matrices. So that one's not too bad. And then finally, the three invariants. So luckily for us, Mathematica has the trace already defined. So the trace function isn't trace, it's actually just TR. So for invariant 1 of M, I can just go TR and then square brackets of M. So that'll find me the trace of M, which is again the same as invariant 1 of M. I'm going to skip down to I3 because we already know that the third invariant is the determinant of a matrix. So for the determinant in Mathematica, we can just go det, capital DET of M. That'll give us our determinant. The second one, the second invariant, this is where we're going to kind of have to use a little bit of formulas. So we know that's 1/2. So in Mathematica, I just go 0.5. And now I'm using the star because I'm multiplying a scalar by scalars. I'm not multiplying any matrices. So now I go star, so multiplied by. And then what I want is invariant 1 of m squared, so that's the same as the trace of m squared, minus the trace of mm. So what I did there for the trace of mm is I just had the matrix M in there, and then I multiply it so that you see that little dot. That means I multiplied it with itself m. It's the same as invariant 1 of mm. So these are the Mathematica commands you guys can use to figure out the invariance. So now it depends how cheeky you guys want to be. So we already know that m and m prime are going to have the same invariance. And the question asks for the invariance of m and m prime. So you guys can either calculate both of them. If you guys are using Mathematica, this will take 10 extra seconds out of your lives. Hopefully that isn't too bad, but I guarantee a lot of you guys are just going to find the invariance of m and throw them in as the invariance of m prime. So it's perfectly valid, but you should probably do it just to check, because it's a great way of determining if you got anything in your matrix wrong. So that's kind of my little tip to you guys. And with that being said, that concludes question number 4. So again, I hope you guys found this helpful. That's what these videos are there for, to make it more helpful. I hope I'm not creating more questions than answers, because that'd be the exact opposite of what I'm supposed to do. So yeah, I guess with that being said, thank you guys all so much for listening. I will see you guys in question number 5.